Hello, my name is Fletcher. I am with CSA Group, and I currently manage the Lighting Center of Excellence located in Irvine, California. Today, I'm going to be talking to you about horticulture lighting, and more specifically, some of the ways that solid-state lighting is applied to plants. So we'll start by discussing what exactly is horticulture lighting. The simplest definition of horticulture lighting is that it's artificial light that's used to stimulate plant growth. It's typically either applied as the sole light source, or it can be paired with the sun as a supplemental source. Lighting is designed and regulated to help plants to say produce more aesthetically pleasing flowers and leaves, or to produce more fruit, or to adjust the growing time. And you end up with these light recipes, which is a color combination of the luminaires within a lighting system. These recipes are developed to suit different plant species through an understanding of their photobiological responses. So now we'll look at the effects of horticulture lighting. The relationship between plants and light is complex and crucial, namely the way that these organisms absorb and utilize various nutrients based on light signals. The light, the quality, the intensity, the duration, they all affect and influence the mechanisms that plants perform in the various stages of their growth, such as nutrient uptake, which impacts morphology, fruiting, flowering, etc. Now, one of the most crucial components is the spectral distribution, or the wavelength of the luminaires. It's arguably the most vital part of a horticulture lighting system. Plants basically can discern wavelength of light to which they're exposed and enact appropriate physiological responses using sensory photoreceptors such as phytochrome, cryptochromes, phototropins, the UV. There's also the UVB photoreceptor, which is UVR8. And these photoreceptors observe light and introduce wavelength-specific responses. So, for example, phytochromes may respond primarily to red and far red parts of the spectrum, and they're involved in processes like germination and branching. But meanwhile, cryptochromes act as blue light and ultraviolet light receptors, and they help to regulate the circadian clock. There's been quite a few studies that show that different wavelengths do indeed change the nutrient uptake of plants, and that different species have different responses to the same wavelength. So it's very plant specific or species specific. But the light intensity and duration of exposure also play a key role in plant growth. The photosynthetic effects of plants changes significantly with the variations in light intensity, which leads to dynamic changes in sugar accumulation in plants, for example. Additionally, these changes of photoperiod, which is essentially like a day that's perceived by the plant, the photoperiod. Plants show different physiological responses relating to germination and flowering. So that brings us to tunable horticultural lighting sources. Technologies that incorporate tunable spectra are ideal for taking advantage of our ability to affect plant production. So unlike other forms of light, the color of tunable light can be controlled digitally and accomplish we accomplish this through solid state lighting technologies. While traditional light sources, they employ electrical filaments or plasma or gas as a source of illumination. Solid state lighting is a form of lighting where light emitting diodes or LEDs are used. And LEDs operate due to a phenomenon of electroluminescence, which is basically the process by which light is emitted directly from a current flowing through a material. We could go deeper into this, but that would be a completely separate topic. So a properly managed environment can be used to adjust a plant's nutrient absorption capacity, which can ultimately lead to a greater yield and a greater economic value of the crops. What are the benefits of using LEDs? With their narrower wave bands, you can actually match wavelengths to the plant's photoreceptors, again, species specific, to provide optimal production without wasting energy on non-productive wavelengths. Let's see, LEDs produce high light levels with low radiant heat output when they're cooled properly. They can turn on and off almost instantly with no warm-up time required. So let's say, for HPS technology, high pressure sodium lamps, they can take up to 30 minutes to reach their maximum output. So let's say the application is supplemental lighting in a greenhouse. Well, when the sun goes down, let's say you're looking to extend the light exposure by 30 minutes. Or let's say, it is during the day and a cloud goes in front of the sun and you'd like to supplement the light. Well, if you've got a 30-minute warm-up time, that's obviously not desired. So the nearly instant turn on of the LED product is definitely more desirable. Let's see, LEDs have become much more affordable over the years. So economically, their performance to cost ratio has increased. And I think that efficacy is one of the biggest advantages over older technologies. So for every electrical watt in, you're producing more photons that are coming out and less thermal watts as well. So when you're talking about an enclosed environment, an indoor indoor growing space, there's fewer watts to remove from the space, less heat to be extracted. And lastly, the increase in smart lighting in solid state lighting products has provided benefits through automation. So that's definitely something that's on the rise. So now we'll look at some of the standards in horticulture lighting. And we will start with safety. So one of the most commonly applied lighting safety standards in the US is UL 1598. And it outlines the requirements for luminaires used in non-hazardous locations. But UL 8800 applies specifically to horticultural lighting systems. And 8800 refers directly to 1598 for all of the testing requirements, but it also adds a photobiological safety evaluation. Typical testing conducted under 1598 includes electrical testing, temperature testing, rain testing, humidity testing, dielectric testing, ground bond testing, strain relief. I could go on. It is a pretty big testing regime. And then the IP rating or ingress protection is a supplemental rating that it has no bearing whatsoever on the North American certification, but manufacturers often request to get an IP rating due to the more aggressive environments in horticulture applications. So back to the previously mentioned photobiological safety evaluation. It is required by UL 8800 in the form of an IEC 6471 test. And the main objective of this evaluation is to protect the people that are working in these environments with the plants. The 62471 applies only to human eye and skin safety. So first, there's weighting functions that are assigned to different wave bands in the spectrum because for some wavelengths that are outside of the human eye response range, if these products are producing those, the issue is that those wavelengths don't provoke an aversion response reflex. So you don't necessarily know that you may be harmed by these wavelengths. And then algorithms are used to determine the risk factor on the luminaires. Based on that risk factor, a given luminaire is assigned to one of 4 risk groups. So there's exempt, and then group 1, group 2, and group 3. Group 3 being the, let's call it the least safe. And for all of the non-exempt risk groups, manufacturers are required to provide PPE specifications that, whether it's a pair of filtered glasses to protect your eyes, or perhaps something that you need to wear over your skin if you're being exposed to this light. And at this time, group 3 will prohibit you from being able to certify it to UL 8800. So that one's again the least safe of the groups. And then we've got the performance side of it. So that was the safety side. Now on the performance side, the Design Lights Consortium, DLC, is an organization that really sets the performance standards for the lighting industry in North America. And horticultural lighting, they've got a specific specification for horticultural lighting products, and the tunable, spectrally tunable products are certainly on their radar. So they've got some requirements around that. Some of which are that the manufacturer provides user-facing documentation that narrates the control protocol and input parameters employed by in controlling the output. And then there's an LM79 test, an IES LM79 test report for the manufacturer design, and it states the highest power consumption. So if it's a spectrally tunable product, we're basing the efficacy on the, let's call it the worst case scenario. So when the most LEDs are on at the highest power. And then that IES LM79 sphere test measures the spectral output for each of the channels or control levels that are used in the products. And then you've got an ISTMT test, which is an in situ temperature measurement test. It's performed on the hottest of each of the LED types at their highest output. And that is used to help determine the lifetime claim of the product. So, as LEDs are run inside of the luminaires at high levels, high temperature levels, that decreases their life. The cooler it is, the longer they'll last. So we go in and do an actual measurement of the hottest of each color to determine what the maximum lifetime claim can be for the luminaire. And these are all things that we do execute in our Lighting Center of Excellence in Irvine, California. These safety tests and performance tests, among other things. But we certainly do so for the horticultural lighting products as well. Got some references here. And that's it. Thank you for listening. I hope it was helpful and beneficial.